I'm very pleased to introduce Roman Fasel. So thanks a lot for agreeing to give a talk to us. And so let me very briefly introduce Roman before I give the floor to him. So Roman got his PhD from University of Freiburg, working on real surface science experiments, so photoelectron diffraction, angle resolved photoelectron spectroscopy, and things like that. Then he went to do a couple of postdocs in La Trobe University in Melbourne, and then at the Fritz Haber Institute in Berlin, before going back to Switzerland and joining the EMPA, the Swiss Federal Laboratory for Materials Science and Technology. And he's there still. He's now the head of the Nanotech at Surfaces Laboratory at EMPA, and he's also a professor at the University of Bern. And Roman's group is doing research on is one of the most prominent groups in the field of on-surface synthesis, I would say. And you probably are familiar, or at least you should be familiar with his work on these graphene nanoribbons that you can create using on-surface synthesis, starting from the famous 2010 Nature paper. And there's of course been plenty of results after that. So I think the group focuses on low-dimensional graphene-related nanostructures, molecular nanographenes, carbon nanotubes, nanoribbons, and also some 2D polymeric systems. And they have a particular emphasis on engineering electronic properties by developing synthetic protocols that allow fabrication of specific atomically precise nanomaterials using these various kinds of on-surface routes. And this has created, I think, several extremely fascinating results, and we will hear more about this today. The title of Roman's colloquium is Engineering Intrinsic Pi-electron Magnetism in Atomically Precise Carbon Nanostructures. So with that, Roman, please.
Thank you very much for the kind introduction, Peter. And thank you very much for organizing this very nice series of colloquia that give us very good motivation to get an early coffee on Monday mornings and be ready at 10 o'clock. And I'm happy to have the opportunity here to talk about some of our recent work. It's actually most of what I'm going to show is the work of Shantanu Mishra, a PhD student that recently defended his thesis. So he should in principle be the person giving the talk, but I will try my best to live up to the standards he has set in his PhD work. Let me start with a little bit of background. So as Peter correctly pointed out, we have been involved in this field of on-surface synthesis for quite a while. During the last 10 years, I think this was our main focus. So what is on-surface synthesis? Let me briefly give you a flavor of what we're doing here and why. So the main idea is that we are trying to grow carbon-based nanomaterials by exploiting, first of all, chemical synthesis. So we have collaborations with a range of synthetic chemists all over the world, I would say. They are very good in making all sorts of different molecular building blocks that we then deposit on metal surfaces, mostly under ultra-high vacuum conditions, where we can activate them either by thermal stimulus, or could also be tip-induced, could be light-induced, can be a dehalogenation reaction or some other kind of modification of the precursor that then induces some follow-up reactions. And these precursors are programmed, so to speak, that they undergo very specific reactions, forming some desired products. And I think one of the advantages of this kind of synthesis compared to the traditional solution synthesis is that we are not suffering from the limitations of the solubility of the products, which is a limitation that solution synthesis faces. And of course, it has some other advantages, like the possibility to analyze the reactants, the processes, the products, by all these nice in situ methods that surface science provides, like, of course, STM imaging, AFM, spectroscopy, and so on. And here I'm just listing some random systems that we've studied over the last few years. And I would just briefly like to give you one example, which is probably the most prominent one that we have studied, which is graphene nanoribbons. So what are graphene nanoribbons? Essentially, they're just cutouts of a piece of graphene along a particular direction, and such that one of the dimensions is much, much smaller than the other one. So here I show you 4 examples with the corresponding molecular precursors. All of them are halogen functionalized. These halogens, they cleave off when these molecules are deposited on a metal surface and modestly anneal to something like 200 degrees or so. They then polymerize, and in a second step, cyclodehydrogenation is induced. I will come back to that in a minute. That then finally produces these well-defined graphene structures that can have armchair edges, like in the first example, zigzag edges, mixed zigzag or armchair, or also some more recent cases where we have armchair nanoribbons with some zigzag edge extensions. Now, I think the interesting feature of this class of materials is that the properties of the ribbons, they depend a lot on the edge structure. They can be metallic, they can be anything from semiconducting to really insulating. They may exhibit spin polarized edge states, as illustrated in this graph here. They may host topological states in the band gap, so really bands that are formed in the gap, or also in a more recent case, we showed that they can host massive direct fermions. So I think this is a very interesting class of materials, and we had a lot of fun making them and studying them. Now here in the context of this talk, the property that is of interest is the spin. And let me briefly show you an old slide, or 2 slides actually, from the zigzag nanoribbons. So that is actually the protocol that we developed to reach these zigzag-edged graphene nanoribbons. So there's a precursor that has this U-shaped with 2 bromines that allow the polymerization in this snake-like fashion on a gold surface upon annealing to 160 degrees. And if this is then further annealed to something like 350 degrees, all these hydrogens that are yet between these phenyl rings, they are cleaved off, and all these carbon-carbon bonds, they form, including the ones here at the edges where there's a methyl group that cyclizes to the neighboring precursor. So this gives rise then to these atomically precise nanoribbons. And as you can see from this non-contact AFM image, the edges are really the way they should be, and everything is hydrogen passivated at the edges. Now there's one defect here. This is a CH2 edge, so one of these methyl groups apparently hasn't lost the second hydrogen. Now, why is this zigzag ribbon interesting? Because it's predicted to host these edge states that are spin polarized, such that all the spins along an edge are oriented in the same direction, and there's an antiferromagnetic coupling across the edges. And this derives from these flat bands at the Brillouin zone boundary. So there's a high density of states, and there's a spin splitting occurring due to electron correlations. Now, we have been searching for these edge states for a long time, and theory always predicted us something like this. So that's the band structure in a GW type theory framework. It predicted that there should be enhanced density of states at the edges. But there was never a sign whatsoever of these edge states on gold, where we fabricated these ribbons. And the only way to really get some spectroscopic signature of these edge states was to tediously manipulate one of these graphene nanoribbons across 2 neighboring sodium chloride islands. And in this situation where the ribbon is electronically decoupled from the underlying metal, there we could then obtain the spectral features that fit very nicely with the predicted density of states, and also in the DIDV mapping, which gives you a kind of an image of the local density of states, we could then clearly see these edge states. But as I mentioned, theory was predicting that even on gold, there should always, this edge state should survive on gold. It didn't, and we really didn't understand that. And at some point we said, well, what about trying to understand magnetism in these carbon-based structures at the hand of much simpler model systems? So let's go a few steps back and study finite-sized, small cutouts of such a zigzag nanoribbon, and let's see whether we can understand spin physics of these structures in these model systems. And as I will show you in this talk, indeed, for these model systems, we could access the magnetism, and I think we also understand a little bit more now about these systems. So that's the program for this talk. I will try to discuss 3 different scenarios of how to obtain magnetism in nanographenes. One is due to sublattice imbalance, like in the case illustrated here. Then another one, which is a topological frustration, this is the case of so-called Clark's goblet. And finally, the one that is most closely related to the zigzag nanoribbons is polarization of low energy states as an origin of magnetism in nanographenes or nanoribbons. Okay. Can you hear me now again? Good. In the second part, I will then try to address also systems that are now growing larger. So I'll talk about magnetism in dimers of such magnetic molecules. And if there's time left, I'll come back to the nanoribbons and talk about a way to induce spins in these along the edges of such nanoribbons. And the goal there would be to fabricate spin chains. But first, well, what about magnetism in carbon? Is carbon a reasonable material to search for magnetism? And of course, you will say that maybe not, because of course, magnetism is usually associated with inorganic compounds, and mostly, of course, with the D and F elements of the periodic table. And that does not only hold true for real solid state 3D materials, but also in let's say, our field of on-surface physics. Most of what has been done is based on this kind of metals: cobalt, iron, manganese, like in the cases shown here. So what about carbon? Can we expect magnetism in carbon? Or what are the underlying principles? So let me briefly address this. So what does carbon offer? I would say the most important aspect is its chemical versatility. And this is maybe illustrated neatly here just by the 3 different types of hybridization that the states in carbon can undergo: sp, sp2, and sp3. And this is really the reason why it's so important in chemistry, in all organic chemistry, and is the basis for all these fantastic compounds. Looking now much further ahead, well, materials consisting essentially of carbon are expected to be biocompatible. There's a plasticity that may be important later on for devices. But I think in terms of magnetism, what is much more important is that the channels for spin relaxation and decoherence are absent. And this is essentially based on the fact that spin-orbit coupling is very small. Carbon has a low atomic mass, 12, and the hyperfine coupling is very small, because C12 is a 0 spin isotope, and the tiny amount of C13 has a very low value of hyperfine coupling. So this is promising, I would say. There's another aspect which also relates to spins, which is the high spin stiffness that is predicted. And this concerns in particular the stability against transverse spin excitations, from which one would expect a long spin correlation length. Last but not least, once we would have a carbon-based magnetic material, it should be possible to control magnetization via electric field. And that is, of course, something that is very appealing in terms of device operation. There has been various scenarios for that proposed in the literature. Here I just illustrate the half metallicity in nanoribbons. That's I think the oldest one from 2006. But there is more recent ones. Most recent one I think is from Ricardo Ortiz and colleagues that was published in 2 years ago. Now, let's consider the electronic structure of small units of graphene, so these so-called nanographenes. How can we understand this electronic structure? Well, as illustrated here, the electronic structure of nanographenes is well described by the tight binding and Milne-Field-Hubbard models, which provide a very good balance between a clear understanding and also a relevant description of the low energy structure. The model, the tight binding model, of course, is based on the assumption that in the vicinity of a lattice site, the Hamiltonian can be approximated by the corresponding atomic Hamiltonian, and that contributions to the potential energy term from the remainder of the lattice can be treated perturbatively. So this is then this first term, which is characterized by this hopping parameter T, and electron correlations can now be included with the so-called Milne-Field-Hubbard model, where the relevant parameter is given here. So this is this U, this is characterizing the on-site Coulomb repulsion. Now let's apply this to 3 different nanographenes that all consist of 6 fused rings. And in the first case, they're just fused in this up-down fashion. This gives rise to armchair edges. Then we have the case of the hexacenes. They're linearly fused. We obtain zigzag edges. And finally, this small 2D flake, the trianguline, which is such that the rings are fused to give rise to all zigzag edges. What's now the expected electronic structure? Well, it turns out that if we apply now this tight binding model, that the armchair edged fulminine has a pretty large HOMO-LUMO gap of about 2.5 eV. This reduces dramatically just by going from the armchair edges to this linear fusion with zigzag edges, the hexacene. It collapses to almost to less than 1 electron volt. And most spectacularly, just going now to the trianguline, what we find now is 2 zero energy states. So this shows already that just by geometrical considerations or tuning the shape of a small graphene flake, one can obtain very, very, very different properties for these resulting nanographenes. Now, what happens if we switch on correlations? So this U-turn, we go now from the tight binding to the Milne-Field-Hubbard model. And what happens is that the zero energy states, they will spin split. So what we obtain at half filling is 2 singly occupied molecular orbitals that are occupied and 2 singly unoccupied molecular orbitals. So there's a symmetry breaking. The spin is not symmetrically distributed anymore. So there's spin on the blue spin is on one type of lattice site, and the red spin is on the other type of lattice sites. There is some simple rules that allow to predict for such nanographenes whether there is zero energy states. So this is the first rule given here. This rule derives from simple benzenoid graph theory, and it tells us that the number of expected zero energy states is just twice the maximum number of non-adjacent carbon atoms in the system minus the total number of carbon atoms. So for instance, for trianguline, if we consider this molecule and the 2 sublattices A and B of the underlying graphene honeycomb lattice, here we can count that there is, you can find a maximum of 12 non-adjacent carbon atoms, meaning a set of atoms where none of the members is a neighbor of each of the set. And the total number is 20, well, the total number is 22, so the difference is 2. So we're expecting 2 zero energy states. There's another rule that tells us how the spins that belong to these zero energy states, how they couple. And this is going back to Ovshinnikov, and it has later been extended by Lieb, so it's usually called Lieb's theorem. It tells us that the resulting spin of such a nanographene is just 1/2 the sublattice imbalance, so the difference between the number of A sublattice atoms and the B sublattice atoms. So in this case, for trianguline, we have 12 of the black atoms, we have 10 of the white atoms, so the difference is 2 divided by 2 gives us a total spin of 1. So that already predicts us, we have 2 zero energy states, a total spin 1, so that will predict that this is in a triplet ground state. Now this can also be done for this molecule here, this bow tie shaped molecule. In that case, it's a little bit more complicated to sort out what is the maximum number of non-adjacent carbon atoms, but it turns out that we expect also 2 zero energy states. And the sublattice imbalance tells us that the resulting spin should be 0. So here we expect a singlet ground state. So we expect an antiferromagnetic coupling of the spins. Now these are very simple rules, and they allow us to really, via just geometrical considerations, to tailor the magnetic properties of these nanographenes. Now, let me come to the various scenarios that are around regarding magnetism in graphene and nanographenes. They revolve essentially around 2 main concepts. The first, and conceptually, I think the simplest route to induce magnetism in carbon is to create a sublattice imbalance. And per Lieb's theorem that I just mentioned, this translates directly into spin imbalance. This scenario has been realized, for instance, in graphene by creating an atomic vacancy. This removes a pz orbital from the pi system, and we are left with an unpaired electron, and this creates a spin at this lattice site. The same can be done by dosing hydrogen, so we passivate or we turn one of the carbon atoms sp3. This removes the corresponding electron from the pi system, and again this induces a local spin. Now for finite size nanographenes, the same can be done. So there is nanographenes that inherently, so due to just their structure, they have a sublattice imbalance, like the trianguline that I discussed before. This has been realized by the group of Leo Gross a few years ago, and they can clearly see these positive ion resonance and negative ion resonances that are attributed to Coulomb splitting due to spin separation. Now, departing from this notion, there is also a prediction that it is not necessary to have a sublattice imbalance to have unpaired electrons in these nanographenes. And this is then what is called topological frustration. The underlying reason is that for specific shapes of these nanographenes, it's not possible to pair all electrons into pi bonds. There's always some of the electrons that are left, and this of course also then leaves us with unpaired electrons and therefore potentially magnetism. The second or third distinct concept is polarization of low energy states, like in the case of the graphene nanoribbons that I briefly discussed in the beginning. Here we don't rely on true zero energy states, but on states, on these edge states that are close to zero energy. And with increasing system size, these approach the Fermi level, and at some point they may undergo spin polarization. This has been observed recently by the group of Nacho Pascual in certain junctions between chiral graphene nanorings. I will come back to that in a minute. Of course, I should mention that there is also recent evidence of ferromagnetism driven by electron correlations in bilayer graphene, but this is a different story that I don't want to enter here. Good. Let me now go through some examples of these different scenarios. And I would like to start with the conceptually simplest one, which is the creation of sublattice imbalance. I already mentioned these triangulines. They are interesting because they lead to high spin ground states. So the smallest one is the phenylenyl radical. It has a spin 1/2. The trianguline, the classical trianguline, has a spin 1 ground state. And we have been aiming for this pi-extended trianguline, as we call it, or also 4 trianguline, because it has these 4 zigzags at the edges. So this is predicted to have a spin 3/2 ground state. And the way to make it via on-surface synthesis is to find a good precursor, which in that case is the one shown here that was provided by our chemistry friends at TU Dresden. When we deposit this precursor on a metal surface, and it's gold in this case, and heat it to 320 degrees, we find that something like 17% of all the products are the targeted pi-extended triangulines. So this is an STM image. Here you have a CO image, so a low bias image with a CO functionalized tip. And it turns out that everything is the way it should be. DFT tells us that the molecule is flat. It's very weakly interacting on the surface. So we would expect to be able to probe the intrinsic properties, at least to some extent. I should mention that the remaining products are mostly fused species. So you can imagine that having these 3 unpaired electrons turns these molecules pretty reactive. And that's indeed what we see. They tend to fuse together. And that's the reason why the yield is only 17%. But of course, for STM, this is not a problem. You find the molecule that you want to study and you go for it. But let's first consider what we would expect in terms of properties for these molecules. Tight binding tells us that there should be 3 non-bonding zero energy states, which spin split when we go to the mean field Hubbard model. So introduce the on-site Coulomb repulsion of 3.5 eV. So we have 3 SOMOs, and the ground state is predicted to be a quartet. So this spin 3/2 ground state. When we do the spectroscopy, indeed, we can detect these SOMO and SUMO states with a Coulomb splitting of about 1.5 eV. Mapping of these orbitals gives us the maps that I'm showing down here. This is topography. The central panel is the DIDV maps. And you can see that these are very, very similar to the tight binding computed LDOS maps. There's some further support that these are indeed the spin split and Coulomb split singly occupied states, which comes from comparing this Coulomb gap to what one would expect from theory for this open shell quartet ground state. We have to refer to somewhat higher level calculation because correlations are important, so DFT will not give you a good number. If you do that in the GW approximation, and we also take into account the screening of the underlying surface, we take this into account in an image charge model, then we get a value of 1.67 electron volt, which is in very good agreement with what we actually measured. So we are very confident that this is really the quartet ground state that is retained on gold.
Yeah, Roman, there's a question from Daniel.
Yes.
Daniel, please go ahead.
Yes, I have a quick question. So if I look at your DIDV maps, the one at negative energy actually looks relatively nicely symmetric, as does the STM topography. Now for the positive map, it looks quite distorted, although the topography at that same energy is still fine. Is there any explanation for that?
This is just the asymmetry of the tip. I mean, you can also see in the negative, you can see that the upper two lobes, they are stronger than the other two. And this is more pronounced in the positive bias, which is where the signal to noise is worse. But this is purely experimental.
Okay, so for other tips, then this changes.
The other tips look, well, this is the most symmetric we got. If you take another tip, it may look much more asymmetric or at least differently asymmetric. So we are convinced that this is not intrinsic.
Okay, thank you.
One thing you may wonder is why we do not observe any spin excitations. So one would expect the first excitation to be a quarter to doublet excitation, and we don't observe that. There is some reasons why this, I could give some reasons which make this plausible, but I don't want to enter, I don't have the time to enter in details here. Maybe I can answer it in the questions. There has been a similar case that has been investigated by the group of Nacho Pascual. This is also a trianguline that is extended now in a different way. It has these 3 rings that are fused at one end. This is expected to have a spin 1 ground state. And the interesting aspect here is that this was, despite being a spin 1 ground state, they could observe this Kondo peak. And they explained it very nicely to derive from an underscreened Kondo state in this mammography. But also there was no spin excitation that was detected. So I think these triangulines, they retain their grounds, their spin state on metal surfaces. So there is evidence that this is the case, at least for the 3 and the 4 trianguline. More recently, there has also been work published on the 5 trianguline. So this is having a spin 2 ground state. And we are working on a spin 3 ground state. So this is the 7 trianguline, which is already a pretty big beast. So I think the triangulines are interesting because they really allow to go to high spin ground states. Good, so let me come to the second class of nanographines, or the second scenario for inducing magnetism, which is topological frustration. For the trianguline that we just discussed, the sublattice imbalance is inherent. That leads to spin, but it has been recognized a long time ago, in the 70s, that it's not necessary to have unpaired electrons to have an intrinsic sublattice imbalance. That there were molecules like these illustrated here, where you could do whatever you want. You can try as long as you wish to draw an alternation of single bonds and double bonds, and you'll never manage to do that without leaving unpaired electrons. So these are non-Kekulé nanographines due to topological frustration. They are sublattice balanced, but despite this fact, they have intrinsically these unpaired spins. And of course, they are difficult to make in organic chemistry in solution because they're reactive. And on-surface synthesis helps here. So we designed this precursor with 4 methyl groups at the central phenyl ring and 2 anthracene at the ends. That is designed to cyclize into this so-called Clark's goblet on a gold surface. And indeed, that's what happens. So these are Stm Overview Images of the products that refined after annealing to 300 degrees. What you can see is that there is 2 species that look somewhat different. Let's first focus on the fully symmetric species 1. This is CO imaging, but Laplace filtered in this case clearly tells you that the molecule is the way it should be. And we can therefore ask, what is the electronic structure? Does it really have these two unpaired electrons? So tight binding shows you this. Spin polarization induces this Coulomb splitting into singly occupied and unoccupied states, where now the interesting feature is that one of these states is totally localized on the left end. So the one spin is like localized entirely on the left part of the molecule, and the other spin is localized on the other side of the molecule. And the coupling is antiferromagnetic. Now, can we see this in experiments? So if we do the spectroscopy, we can find the HOMO -1, the LUMO +1, +2, we can map them, but the SOMO and SUMO, they are there, but they're pretty broad. So it's much easier to see in the LDOS maps, which I highlight here. So you can see the experimental LDOS maps in the top part and the computed ones, tight binding in the bottom one, and they agree reasonably well.
Roman, there's a question by Agustin.
Yes,
please go ahead.
Hi, Roman, can you hear me?
Yes.
Just quickly, how can you justify such a large U for a system where the states are quite delocalized?
How can you justify such a large U? This is not a large U, so this is a standard, I would say, U for graphene-derived systems. 1.6 T is roughly the standard value. So I would not qualify this as a large U.
Mm-hmm.
And I mean, even for gas phase situation, this is a very reasonable value of U. Now, what this U means when you have your nanographene on a metal surface is yet another question. And I think nobody can tell you what happens with the U in this case. But even irrespective of that, I think this is a very reasonable value for U.
Okay, yeah, thanks.
Okay, so let's focus to close to zero energy, because that's where we would expect maybe some features related to the spin. And indeed, what we find in this case is these symmetric step-like features that are therefore due to some inelastic process. They're exactly at ±23 millivolts, and we attribute them to the excitation of a singlet-triplet transition of 23 milli-electron volts. Why are we convinced that these are indeed spin excitations? Well, there's a number of arguments that I'd like to briefly outline. One is if we fuse two of these molecules together, what would we expect? Well, we would still expect the two spins at each end, but now they're spatially separated, and we would expect the coupling drop to essentially zero. And that's indeed what we observe. So these fused species, they are observed, just they are there because the molecules are reactive. When we do spectroscopy at the ends, what we find now is this peak at zero energy. So that's a clear signature of a condo. This can be verified by changing the temperature. It's broadening like one would expect it from a condo with a condo temperature of 37 Kelvin. And we were lucky to get some collaboration with the group of Peter at Aalto University, where we could see that in a magnetic field, we can see the Zeeman splitting of this peak arising at, well, 10 Tesla was just enough to see the splitting. So this means that, yes, the spins are there. There is no features that we could attribute to inelastic, to vibrations that could explain the spin excitation that we see, or that could be the reason for this inelastic feature. So we are pretty convinced that this is indeed a spin excitation. There is more arguments, like a second species of molecules that we find that looks a bit different at one end. What is apparently seems to be missing is the apex of one of the terminal rings. And if we do spectroscopy on these features, on these molecules, we also see this condo feature. We don't see anymore the spin excitation. However, this can be verified that it's a condo. However, if we now give the molecule a slight kick with the STM tip, we recover the spin excitations. And what is the reason is that the molecule that looks asymmetric is located at an elbow site of the herringbone reconstruction. And therefore, we assume that it's binding to a low coordinated gold atom. This, of course, removes this π-electron from the pi system, and we are left with a spin 1/2 system that gives rise to condo. And if we give it a kick, we recover the original molecule with the 2 spins, and therefore the spin excitations. The same can be done with some molecules that have an additional hydrogen, because this is a reactive site, it may catch an additional hydrogen from the rest gas. Also in these cases, we see a condo. We can cleave off the hydrogen, we recover the spin excitations. So I think there's a series of proofs that these are indeed singlet triplet spin excitations. Actually, if you look at these spectra here, switching the condo on and off, this looks strikingly similar to spectra that were measured in Nacho Pascual's group for these nano-ribbon junctions that I mentioned earlier on, where also they could switch from one situation to the other by removing a hydrogen that was bound to one of these positions. Okay, so to summarize this part, I think here we have an interesting magnetic system. It's due to topological frustration. It has a robust magnetic antiferromagnetic ground state that is 23 millivolts. The spin excitation is at 23 millivolts, so that should be stable even at close to room temperature. Good. Let me then come to the final.
Roman, sorry, there's a question by Daniel. Daniel, please go ahead.
Yeah, sorry to interrupt once more. So did I understand it that your, what is it called, class goblets, the bow tie molecule, there you do see basically that there's spin and you can see that on bare gold, on a bare gold substrate. Yes. But for triangulin, you do not see any signature of the spin. Did I?
Well, we see the spin split, singly occupied and unoccupied orbitals.
Yeah, but you do not see you don't see a condo, for instance.
No. We would not expect to see a condo because you have coupled spins. It's not a spin 1/2 system. It's a spin 3/2.
Yeah, but you also do not see any indication of spin excitations in those molecules. No. Do you have any idea why these two molecules act so differently?
The next excited state is predicted by high-level theories to be very high. It's about at least 500 milli-electron volts higher than the ground state. And this is far, we believe this is too far to be seen on top of all the other contributions that you have in the spectroscopy. So this is going close to or into the tails of the elastic peaks, or the SOMO and the SUMO. And we believe that this is the reason why this cannot be seen.
Okay, thanks.
Good, so let me address this polarization of low energy states as a reason for magnetism in these nanographenes. The goal here is to have nanographenes that have all zigzag edges, because these states close to zero edge states are related to these zigzag edges. We've seen the triangulin case. There is in the literature, in the chemical literature, there is quite a few works, but like for the periacenosines or the circumarenes, like shown here, but they're all closed shell. So probably they're too small because spin polarization sets in with increasing system size. So we're aiming here at large, the rhombus-shaped, all zigzag nanographenes. We call them rhombines for their shape. And we add a number that gives the number of rings fused along one of the edges, so the 4 and the 5 rhombines. Now, synthesis works quite well. So the 4-rhombine on gold, we see indeed a yield which is very, very high, almost 100%. So this doesn't seem to be reactive. Well, might suggest that this is closed shell. On the other hand, the 5-rhombine, we find that they're all fused together, and it's very, very difficult to find individual ones. Well, they can be found, but they're very rare. We have to go to copper 110 to have a high yield, but of course there the interaction with the surface is very strong, and that's not where you would expect to then detect the magnetism. So we focus on the case of gold, even if the yield is low. But the reactivity here may already suggest that this is open shell. So what does theory predict us? Well, it indeed predicts at the FT level of theory that the 4-rhombine is closed shell, and there's a transition to open shell somewhere between 4 and 5. So the 5 is expected indeed to be the first one that is open shell. Now, what does experiment tell us? Well, for the 4-rhombine, indeed, we do not find anything too interesting. There is just the usual HOMO and LUMO peaks that are well understood. So this is really closed shell. For the 5-rhombine, however, we do see at low energy these step-like excitations that are clear, that are at 102 milli-electron volts. So this seems to be huge. So let's try to understand what this is. If we refer to theory, and in this case, we need to go to some complete active space calculations to take into account really a quantum ground state of this species. What this theory tells us is that indeed, for reasonable values of U, the singlet to triplet excitation is on the order of 100 milli-electron volts. So this fits very, very well. Also, if we compare the energy, the Coulomb gap that we observe by SDS of 900 milli-electron volts to, again, a GW calculation with image charge corrections, this agrees very, very well. So indeed, this seems to be a case where we have a huge exchange coupling of 100 milli-electron volts between the spins at the two edges here of this molecule. So theory and experiment agree very well in that case. Good. So let me just summarize this part before I should, well, almost come to the end, I guess. I think I could, or I hope I could show you 3 different scenarios of magnetism in nanographenes. One here based on topological frustration. One due to sublattice imbalance. So this is the case that produces the high spin ground states. And the last one here, the polarization of the low energy states, where with increasing system size, these close to zero states, they get spin polarized. And this can lead to very strong exchange coupling in the case here of the 5-rhombine. So, okay, but what about spin chains? So these were nanographenes, but we would like to make spin chains. So could we imagine, rather than using metal atoms and moving them around with the STM tip to assemble a spin chain, could we use maybe on-surface synthesis to make something like that? So I hope I convinced you that at least we can create magnetic nanographenes that carry a spin. So what about coupling them into a chain? And let's look at the first step along this endeavor. The first step, of course, is just let's couple 2 of them. If we can couple 2, maybe we can couple 3 or n. And we refer to the triangulene with the spin 1 ground state. And the precursor in that case is illustrated here. That should result in this triangulene dimer. And indeed, this works very well on gold 111. Now, what about the expected properties of such a dimer? What I show you here is for triangulene and the dimer, first the tight binding states, so 4 zero energy states for the dimer. That spin split, so there's a Coulomb gap. We have now spin on one triangle and there's another spin on the other triangle when they're covalently connected via this minority sublattice atoms. This can now be expected to be a spin 1 Heisenberg dimer simply because in the triangle as such, we have a spin 1 ground state that is significantly lower than the closed shell first excited state. That was the 500 millieV I just replied to the question of Daniel a minute ago. So we would expect that the coupling within the triangle is much stronger than the coupling between the two triangle units. So we would expect from the Heisenberg model a sequence with a singlet ground state separated by the effective exchange interaction to the triplet, and then twice the same energy to the quintet. And this is confirmed by a complete active space calculation where the level sequence is also such that we have 1 JF for the singlet triplet and 2 J effective from the triplet to the quintet. Now, what does experiment tell us? We see a Coulomb gap of about 1.65 eV with clear SOMOS and SUMOS. We also see clear spin excitations, and they're now at 14 milli-electron volts. So the exchange coupling between these two units seems to be on the order of 14 milli-electron volts, which actually is not that far from what one would expect from this CIS66 calculation. So this red line here is the 14 milli-electron volts that we observe experimentally. So what we believe this shows is that indeed we have here a collective ground state in this triangle dimer, and this raises hopes that this could be extended to trimers and tetramers and spin chains ultimately. Ah, well, yes, I forgot the spin excitation map that one can of course measure on this 14 milli-electron volt peak, which should look similar to the singly occupied and unoccupied molecular orbitals, and it does look exactly like these orbitals. Now, I think the interesting aspect about playing with molecules is that this exchange coupling can be tuned over a large range. So I showed you Clark's goblet with 23 millivolts, the triangle dimer 14 millivolts. If we introduce a further Fresnel spacer, it goes down to 2 millivolts. It can be linked not in the straight fashion, but in the angled fashion. Then it swaps from antiferromagnetic to ferromagnetic coupling. Or I also showed you this case of the rhombine, where the coupling is much stronger. It's about 100 milli-electron volts. And I think this, let me skip this. This really raises hopes for all carbon spin chains and lattices, where the building blocks can be tuned. So they can be tuned to tune the sign and the magnitude of the exchange, the total spin. We saw this high spin ground state in the triangulines, the low spin for the other cases. The covalent bridge will also have an impact on the sign of the exchange. So like swapping from a linear to an angled connection, changes from antiferromagnetic to ferromagnetic. Of course, the longer the connection, the weaker the exchange, and so on. So I think the attractive features here is that these are chemically tunable parameters. And we are working along these lines. So this is a first STM image, CO image of a spin chain, what we believe is a spin chain. So these triangulines now connected in a linear fashion in not only two, not only a dimer, but really a long, long chain. Okay, I think my time is up. More than up. I will therefore skip this last 4 slides on the way of inducing magnetism in these nanoribbons, and just come to the conclusion. So I hope I could give you a flavor for magnetism in nanographenes. I hope I could convince you that this can be extended to larger systems. Overall, I hope I could address this question mark here besides the magnet and replace it by an exclamation mark. And, I think for me, the attractive feature of this field is really that is the chemical tunability of the magnetic interactions in terms of sign and strength. And maybe ultimately the expected long spin correlation lengths and decoherence times that of course have to be confirmed. These are just predictions. Of course, this will be a very, very important goal to confirm this at some point. With that, I would like to thank in particular Shantanu Mishra. So all the experiments that I showed you, most of them, almost all of them, I should say, are coming out of his PhD thesis. Chang was the one with the part that I didn't show you, the nanoribbons. Oliver was involved in much of the theory, as well as Carlo and Christian. Pascal is the group leader of the carbon nanomaterials group. Peter and Chavolieno at Alto were very crucial to have these magnetic field experiments to demonstrate the magnetic origin of this Kondo feature. Joaquin and Ricardo did the CIS calculations, and of course, crucial, the collaboration with the chemists that made all the precursors that we then turn into nanographenes on the metal surface. And thank you for your attention.
Thank you, Roman, for this very nice talk. So now we have time for questions, and I think that there's already a question by Toma. Susi, Toma, please go ahead.
Yes, thank you. Thank you very much. The topic of magnetism in these carbon systems has been long a very interesting one, and it's cool to see that there's this level of engineering possible. And some of the exchange couplings are starting to be fairly high. So could you give like an outlook on the temperature range you think you will be able to reach? I mean, obviously, a lot of the STM work is at very low temperatures, but can we have magnetic systems at room temperature from these structures?
Yes, for sure. The rhombine case that I showed you has an exchange coupling of 102 millivolts. This is way beyond room temperature. This is not even the highest that you may expect. There is one slide I had to skip.
Have you actually measured room temperature magnetic properties of these systems?
No, this is this of course would be very, very interesting. But as you said, I mean, we are here bound to low temperature STM investigations. We didn't even try, to be honest.
Yeah, that's right. Yeah.
But yes, conceptually, what you see here is a range of different nanographenes with peculiar shapes and dimensions n and m. And Clark's goblet is the point down here. And you can see that the exchange coupling goes up to something between 150 and 200 milli-electron volts, which is of course way beyond room temperature and also way beyond what you can expect for metal nanomagnets or metal spin chains.
Good, thank you.
There's another question by Sebastian. Sebastian, please go ahead.
All right. Roman, first of all, thank you. I really enjoyed the talk. I have a practical question. So since as far as I get it, the spins come essentially from radicals. How do you manage that that not everything, every piece of dirt, every defect on the surface, every piece of hydrogen reacts and kills the spin on these molecules?
Yeah, that's a good question. Maybe one important aspect is that these are not sigma radicals, but pi radicals. So the radical is in the pi system. And as you could see from some of the spin density maps, the radicals are pretty delocalized. So it's not such that you have one atom that is the radical, okay? it's distributed over, let's take this one random case here. The spin density is distributed over, and this is the radical electron density, is distributed over the entire molecule, right? So I would say this is responsible for reducing the reactivity. We do find, however, as I showed in the case of Clark's goblet, that sometimes the residual hydrogen may attack one of these atoms and form a CH2, but these are really, really minority species. So we don't do anything special to prevent binding to something. It's not as reactive as you may imagine. Which is also, I think, shown by the fact that the magnetism survives on a metal surface. I mean, these radicals also don't bind strongly to the metal. Well, they don't form a bond with the underlying metal, yes, except at the herringbone sites.
Thank you.
And maybe I have one question. So you said that on the triangulene, the spin excitation energies are so large that basically you don't catch them because you have other features coming up. Yeah. What about then on the extended triangulates? Should the spin excitation energies go down with the size? Or?
Yes, I would expect it to go down. However, to be honest, I do not have any numbers in mind right now. Well, here are the numbers for the extended triangulene. Yes, this 500 millivolts. Yes, these quartet doublet splitting here is for the extended triangulene. And you see here different types of calculations. And you see that the numbers are anywhere between something like 0.4, so 400 millivolts, and almost 1 electron volt. This is for the extended triangulene. For the smaller triangulene, so the 3 triangulene, if I remember well, this is system 3. They are even higher. Well, no, I should be careful. No, I shouldn't claim something that I don't remember which one, but yeah, I may have mixed this up. So that this 500 millivolts is the large extended triangulene.
Okay, thanks.
Sorry for that.
Yeah, so I have another question regarding the artificial chain that you showed. So you showed already results about an effective antiferromagnetic one-dimensional chain, right? And would it be possible to do something like a 2-dimensional Kagome lattice with these graphene islands?
In principle, yes. If you imagine, well, maybe let's take this. If you imagine a triangulene that does not have 2 halogens but 3, you would expect it to connect not only in a chain or in a circle, but also along these directions here. Okay, and that would give something like well, I don't know if I would call it a Kagome lattice here in this case, but it would be a 2D structure, a honeycomb structure of triangulines. And well, one would have to design, of course, the precursor that gives you this kind of Kagome lattice, but I wouldn't claim, I don't think this is impossible. And of course, interesting, yes.
Yeah, all right, I see. Yeah, because it could be interesting, for instance, to try to create some artificial spin liquid with these triangulines. Yeah. Yep, thanks a lot.
Can I have a question? Hi.
Did I hear a question somewhere?
Yeah.
Yeah. Ah, Leo, yeah, go
on. So my question is about how does the surface affect the gaps that you measure? And I think in the calculations, they fit excellent, no? Although I think there's not a surface included, is that correct?
No, the surface is included. Well, are you talking about the singlet, triplet, or the spin excitation gaps, or are you talking about the, let's say, the Coulomb gaps?
No, the spin excitation gaps, sorry.
Okay, yes, they are not included in the calculations of the spin excitation gaps. They are, well, the point, I think, well, what will enter, of course, there is the on-site Coulomb repulsion, the U.
Yeah.
And the U is, I would say, a parameter that we understand not very well. And we understand it even less well for a system that is adsorbed on the surface, where, of course, there may be screening, there may be different things going on that could make the U larger or smaller. I would not claim to have a good feeling for that. I don't know.
In the experiment, have you ever looked at the same system, at these energies for different surfaces? Sometimes you're using also copper surfaces.
We only we're looking on other surfaces in cases where gold somehow did not work out well. We never looked at a system which shows spin excitations on gold also on another surface. That's something that we should do. That's a good point, yes. That may give an idea on how the U or the spin excitation energies change.
Thanks.
Yeah. I think what I would propose here is that we stop the official part, we'll stop the recording, but people who are interested and have more questions can stay online. But so let's stop the official part here and thank Roman once more. Really nice talk. Thanks.